In compliant tendon-driven robotic hands, when tendon stiffness is transformed to passive joint stiffness due to the routing strategies and pulley radii, the joint stiffness forms in unique structures. When joint stiffness is transformed to Cartesian stiffness, the Jacobian, which transforms joint space to Cartesian space, plays a role and thus makes passive stiffness in Cartesian space configuration dependent. We derive stability boundaries for Cartesian stiffness control of compliant tendon-driven robotic fingers, which says that the controller stiffness can never surpass the passive stiffness of the system. To visualize this better, we use stiffness ellipses. As seen here, the blue stiffness ellipse shows the passive stiffness of the finger, which scales and rotates as the finger moves due to the configuration dependency. And as long as the controller stiffness shown in the red ellipse stays within the boundaries of this passive stiffness, the system is stable. However, the same stable stiffness may not be stable at other positions in the workspace due to the configuration dependency. On top of that, when external loads act on the fingers, due to the magnitude and direction of those external loads, the estimation of passive stiffness may vary. Thus, it is important to include the effect of external loads into our stability criteria. And we include a Jacobian-dependent force-based joint stiffness term known as the conservative congruency transform into our stability criteria. And to validate our theory, we predict the stable workspaces for two cases of desired controller stiffness. And as we can see, our system is successfully able to predict the stability bounds for both loaded, unloaded, as shown in left, and loaded cases in the right. In order to improve the stability of such systems, we found that stiffness added in parallel to the actuators at the joints allows us to selectively increase specific desired stability boundaries without increasing the overall transmission stiffness. Thus, we add a parallel compliance term to our stability criteria and use that to optimize a constant stiffness parallel compliance for a fixed controller stiffness in the presence of a fixed magnitude external force acting at all angles at every point in the workspace. Our results gave us values of parallel stiffness that allowed us to successfully increase the overall stable space without needlessly increasing the passive stiffness of the system. Thus, we believe that our analysis and methodology opens the path towards optimizing mechanical design, which is informed by controller stability. In order to learn more about our methods and to watch videos of our results with parallel compliance added to the system, please